Yes. The recording is starting now. And yeah. All right, let me share my screen. And so the format of the session is we're going to, well, first of all, we're going to start off. I have prepared this giant document. I've gone through, oh yeah, before I start, yeah, I probably won't be, it's gonna be hard for me to look at the chat and my computer at the same time. So if you have any questions, like say them out loud. So the first part, we're going to be going over this giant review sheet that I prepared. It doesn't actually have any technical like content on it. It just lists like all the topics. It's 6 pages long. I will be posting this after the session, like probably on Piazza. Yeah, everyone, after the session, everyone, I'll figure out a way to for everyone to figure it out. I'll probably be putting on Piazza and Discord. But the first thing I'm going to, so what we're gonna do is I'm gonna go over all the like topics, and if anybody doesn't understand like something, like you are having trouble with if you have difficulty with like what a consistent versus an inconsistent system is, like speak up. We can go over that. And yeah, so I guess I'll just get started. So module 1, so module 1 is just all the basics, it's like all the basic stuff. I mean, not necessarily saying it's easy, but it's all the like things you need for like the rest of the modules. So it starts off with like linear equations, linear systems, solutions, solution sets, equivalence, row operations. Equivalence just means that 2 linear systems have the same solution set. Remember, the solution set are all the values of like the variables that satisfy the system. So augmented matrices, row equivalents. Augmented matrices, you use them to solve linear systems. And if 2 linear systems are row equivalent, then they have the same solution set. And row equivalence is when you can is when 2 matrices are row equivalent if you can go from one to the other using row operations, using a set of row operations. And remember, row operations are reversible. So then echelon form RREF, just remember all 0 rows at the bottom for both. And for row reduced, for RREF, you need to get all the leading entries to be 1. And both above and below a leading entry needs to be 0 for RREF. And echelon form, you just need below. So like echelon form, you can have like any upper triangular matrix. But for RREF, you need to have like the 1s. And then pivots, pivot columns, pivots just correspond to those leading entries in the matrices RREF. You can also find pivots by just looking at echelon form. So if you're on the exam and you have a question like that, you need to identify pivots. You don't need to go all the way to RREF. And then remember, basic variables correspond to pivot columns, so columns with pivots. So, and then free variables correspond to columns that aren't pivotable. And free variables, they're so special because any choice of a free variable, you can give it any value, and it'll still, and it can still give you a solution to the system. Consistent, inconsistent, consistent just means that the system has solutions. Inconsistent, no solution. And you can tell a linear system is consistent if in its RREF, you don't have a pivot in the row. Yeah. And then when does a consistent system have a unique solution? That is when you have no free variables. And the number of basic variables and number of free variables add up to the number of columns. Yeah, so that's the first part of module 1. That's the very beginning of the course. Next thing that the course goes to is vectors. And the vectors, the definition that was given in the lectures is they're just elements of Rn. So I don't think we need to really go over that. But you can add vectors, multiply them by scalars. linear combinations is a linear combination of vectors is a sum of vectors, and these vectors can be multiplied by scalars. So like 2 times v plus 3 times w would be an example of a linear combination. And you can solve for the weights using an augmented matrices. Yeah, so you can treat it like a linear system if you want to figure out, like, is a vector a linear combination of these other vectors. Let me know if you have any questions again. And then span is a set of all linear combinations of a set of vectors. And spans can be thought also, span can also be viewed geometrically. So for example, a line is the span of just a single vector, and a plane is a span of 2 vectors. And these can be in any like dimension. Like you can have a line in 3 dimensions, and obviously you can't have like a plane in anything lower, like R2 is a plane. But in higher dimension, you can have higher dimensional planes, but that's not really covered in this course. And how many vectors are required to span Rn? N vectors, but they have to be independent. Because you could have like 1, 0 and 2, 0. They won't span R2 because they're just because they're dependent. But if you have like 1, 0 and 0, 1, then you will have a they will span R2. So the next part is matrix vector products. Again, that's just multiplying a vector, left multiplying a vector by a matrix. And the way Dr. Mayer likes to say it is AX is a linear combination of the columns of A weighted by the entries of X. Next, what is so special about the identity matrix? Anytime you multiply a vector by the identity matrix, it gives back the vector. And the identity matrix is just ones on the main diagonal. All ones on the main diagonal, zeros everywhere else. Matrix equation, AX equals B. If B is a solution to AX equals B, then there's a lot of different things you could say. Let me see, what was I trying to say? Hold on. My notes, what was the special thing I was trying to say? Okay. So if B is the solution to AX equals B, then B is in the span of the columns of A, right? You have the solution where you can add up the columns of A to get B. What do we know about A and its columns? If every B is a solution to AX equals B, then we know that, wait, did I say this wrong? What do we know about A and its columns if every B is a solution to AX equals B? We know that, oh yeah, I probably should have said if every, let's see, if every B is a, yeah, well, if every B is a solution, if you can find an X for every B, then you have a pivot in every column. Yeah, every B has a solution. Yeah, if every B, if you can find an X for every B, then that means that you have a pivot. That means you have a pivot in every row. You have a pivot in every row, because there's no way you could have a pivot in the if you have a pivot in every row of A. Yeah. So if you can find an X for every B that satisfies AX equals B, then A has a pivot in every A has a pivot in every row. Yeah, that's what I was trying to get at. Okay, so what's a homogeneous system?
Can you explain that a little more? Like why?
Yeah.
Why?
Okay, so let me let's see. Sorry, I'll disappear for a sec while I stop share. Let me go here. So yeah, this document will be, before I get there, if this document will be made public after the meeting, I'll let you all know. let's see, share screen. Let me share my OneNote. Share. Okay, so if you have a, like a, let's see, let me make a matrix. So if you have a pivot in every row, so let's say, if you have a pivot in every row and you have like A, B, okay, hopefully you, no, that's a bad example. Let me add a couple more. So, so you have a pivot in every row. So you can, like in this case, these two variables, x3 and x4, these last x3 and x4, those would not have, those would be free variables. The main danger is what you don't want is you don't want this. You don't want b. Don't want a non-zero b here, because let's say you had b equals to 1. In this case, you would have 0 equals to 1. And as Dr. Mayer confirmed for us, 0 is not 1. So yeah, that's why you need a pivot in every row. You don't need a pivot in every column, because see here, the extra columns are free variables. So you could have a pivot in every column and it would work, but you also don't. It's just the rows you're checking for, because the rows are what makes having a pivot in every row is what makes sure you don't have this situation where you have 0 equals 1. Does that make sense?
Yeah, that does. Thank you.
Okay. Stop share. Let me share the other share. Okay, yeah. What is a homogeneous system? A homogeneous system is any ax equals 0. So instead of having a b like here, you have a 0. And homogeneous system is just your ordinary ax equals b, where b is not the 0 vector. The special thing about ax equals 0, a homogeneous system, is that that has a trivial solution, the 0 vector, right? So we have ax, let me actually, is the 0 vector. So look right here. If x is 0, it doesn't matter what a is, ax will always be 0, because if you multiply a matrix by the 0 vector, it'll give you 0. So it's called the trivial solution because it's trivial, and it's a solution to all homogeneous systems. However, the special thing is when a homogeneous system does not, what we want to figure out is when a homogeneous system does not have, when a homogeneous system has more solutions than just a 0 vector. And that only occurs when you have free variables, because those free variables can be anything. So you will still have the 0 vector to be a solution if you have free variables in a homogeneous system, but you'll also have other solutions. And that's what parametric vector form is for. You can write the solution set to any linear system. And the difference between, let me stop share. Let me share my OneNote again. Share. So let me erase this. So what was I going to say? So hold on, just lost my train of thought. Yes, parametric vector form for a homogeneous system. H, that's a really bad H, but for a homogeneous system, you'll have like your free variable x2 times like some vector plus free variable times some vector. But for an inhomogeneous system, you'll also have this constant vector. You also have some constant vector. And this vector is what makes it inhomogeneous, because it doesn't have a free variable attached to it. So and geometrically, this constant vector that you add to an inhomogeneous system, it moves. So you can think of the solution set again as like a line or a plane. So normally it's a line or plane that passes through the origin, but this will translate the solution set so it doesn't pass through the origin. Makes sense. Let me get back to the document, share screen. There we go. Okay, and so how do you write a solution? So yeah, make sure you know how to do parametric vector form. That's covered in a lecture. Basically get into RREF and just get into that form. I already talked about that. You could homogeneous system, the solution set will pass through the origin, and homogeneous it won't. So linear independence. So linear independent. So a set. So the columns of A of a matrix, which are vectors, they are independent when AX equals 0 has only the trivial solution. So a set of vectors are independent when there are no free variables to that system. So another way you can, so if vectors are dependent, then you can find, then you do have non-trivial solutions. You do have free variables. And so let's talk about a case where a set of vectors, like the columns of A, include the 0 vector. Then you have any set of vectors that contains the 0 vector is dependent, because you can give all the other vectors a weight 0, a weight of 0, and give the 0. I can only show you. Or should I have to keep on unsharing and resharing? So hold on, let me put my camera down. Sorry, make it easier for me to write. Okay, so like you can think of, think of like this, x1, and then you have some vector v1 plus x2, v2 plus x3, v3, and you need this to equal, and this is just another way of saying that AX equals 0, because those 3 V's, those are the columns of A, and then those 3 X's, those are the entries of the X vector. And the reason why 0, if one of these vectors happens to be the 0 vector, so if these are independent, then the only X values that satisfy this equation are 0. All these X's can only be 0. But if they're dependent, you can have like say 1, 2, and 3, and it's still equal to the 0 vector. So if one of these vectors happens to be the 0 vector itself, like here, it's dependent. And why? Because you can call x1 0, so this cancels, x2 0, this cancels. But then you can give this, say, 2. 2 times the 0 vector is still the 0 vector. So you really just have the 0 vector equals the 0 vector. So that's why the 0 vector always makes a set dependent. And let's see, let me get back to the review sheet. And then if you have just 2 vectors, you can a quick way to tell if 2 vectors are dependent is if one's a multiple of each other. So if you have 2 vectors and one's a multiple of the other one, then you do have a dependent set. And same if you look at higher, if you have like 5 vectors and one is a multiple of another, then the whole set is dependent. And this also can be extended if one vector is a linear combination of a couple of the vectors in the set, then the whole set is automatically dependent. Another way of saying this is if a subset of a set is dependent, then the whole set is dependent. Also, if you have more vectors than entries in each vector, then the whole set is dependent. And this is because, like, say you have all your vectors are in R3, so each vector has 3 entries, and you have 4 vectors. The maximum number of independent ones you can have in R3 are 3 vectors. So if you add a 4th one, you have more vectors and entries, then you have a dependent set. Does that make sense? Probably not the easiest just saying it out loud, but Yeah. So if it's the other way around, if n is greater than m, so like the matrix hat, so the columns, so there's more columns than entries in each column, more columns than rows. That's the whole m versus n stuff. Yeah. Okay. So you can ask questions verbally out loud because it's harder for me to see the chat. But okay. So yeah, the next section is linear transformations, and let me see that. I'll get to this chart later, but you can see here linear transformation is just multiplying a vector by a matrix. For our purposes, all matrix transformations are linear transformations, and linear transformations, they're just the linear transformations. Linear just means that if the sum of the transforms is the transform of the sum, and then multiplying a scalar by the transform is the same as the transform of the vector multiplied by the scalar. So it's like addition and scalar multiplication. That's a theme through the whole course. And so all matrix transformations are linear transformations, but not all linear transformations are matrix transformations. That came up in like module 1 a couple of times. There's like a true or false question or so on that. So domain is just like Rn is Rn. So it's the number of entries in your vector that you're transforming. So if you're looking at like a transform A, you have a matrix A, then the domain is Rn, and then the codomain would be Rm. It's where your final vector, the vector after the transform, how many entries are in that vector. And if you have a square matrix, domain and codomain will be the same, right? Because both are in Rn. And then range is just a set of all images under a linear transformation. So it's just the span of the columns of A, the standard matrix for the transformation. I already talked about.
Can you show an example of this?
Yes. Okay, let me show you an example. Stop share, share screen, share. So we have a transformation, and let's say it's 1, 0, 0, and then we have 1, 2, 0. Okay, so this is our transformation. So T of x equals this matrix times this vector. And this matrix is called the standard matrix of the transformation. So when you have a, so the number of entries in this vector is your domain. So this vector has to have 3 entries, or else the matrix product isn't defined. You can't have like, hold on. You can't have like 4 entries, 1, 2, 3, 4, because then the product isn't defined. So the domain would be R3. And then, oh, wait. I just really butchered that. I'm sorry, everybody.
Do you mean 2?
Yes. I meant 2. Wow, I messed up there. Okay, yeah, 2. Because when you're multiplying, like this has to match this. The number of columns in the first matrix has to match the number of rows in the next one. So the domain would be R2. The domain is R2. And then when you after the product, you'll get 3, you'll get 4, and you'll get 0. And so this is your codomain. R3 is your codomain. You have 3 entries in this vector. And then what would be the range? The range would just be the span of these 2 columns, would just be the span of these 2 vectors that make up the columns of the matrix. Does that make sense?
Yeah, it does. Thank you.
Yeah. Stop share, share again. See final review sheet. Okay, so so first standard matrix. Standard matrix is just the matrix that does the transformation. So it's the matrix you multiply the vector by, AX. So A would be the standard matrix. If you want to, we talk about in module 1, we talked about rotations, reflections, expansions, contractions, shears, and projections. And each one has a matrix that you can multiply a vector by that represents the transformation. And how do you construct them? Well, I mean, first of all, you can memorize them, or you can use standard vectors, and you can use the standard vectors. The standard vectors are just the columns of the identity matrix. So it's like the standard vectors for R2 are 1, 0, and 0, 1. And let me see, I'll pull up my notes and show you what, that'll make more sense. Matrix equations, linear transforms. Yeah. Okay, stop share. Let me share my notes. Okay, yeah. So see, these are the standard vectors. They're the ones with the columns of the identity matrix, the identity matrix. And what I'm saying here is that to figure out a standard matrix, each of the columns are going to be the transform onto these standard vectors. So, for example, okay, good. So, for example, if we want to figure out the standard matrix for a reflection across the x-axis in R2, so let's see x, y. So we're first going to look at the first standard vector, which is 1, 0. And we're going to see, what does a reflection across the x-axis do to it? Well, it does nothing. It's on the x-axis. It won't get reflected across. So we know that our first column of the standard matrix is 1, 0. And now let's look at our second standard vector, which is 0, 1. Yeah, it's supposed to be on the y-axis, so like here. You get my point. So when you reflect it across the x-axis, you just flip it, and now you're here, and now you're at 0, -1. And kabam, this is your standard matrix for a reflection across the x-axis in R2. And if you multiply any vector, so let's say you have a vector 3, 2, so it'll look like this, and you reflect it across, you do the product, and what you end up with is 3, -2. So you just flip the y coordinate. So yeah, that's how you can figure out the standard matrices. You can also memorize them, but if you have composite transforms, it can kind of be useful to just see what the transformation actually does geometrically. So let me share the final review sheet. So yeah. You can also, so with composite transforms, like if it says do a rotation, then a reflection, you can do those for the standard vectors, or you can multiply the matrices in reverse order. So if you have a rotation and then a reflection, you're gonna multiply the reflection matrix. It's gonna be a reflection matrix times rotation matrix times your vector. It's the whole reverse order thing. So next, we have 1, 2, and 1 to 1. They really aren't too much different from things we've done before. 1, 2 is the equivalent of every row having a pivot. So 1, 2 means that there is at least one solution to AX equals B for every B. So we have a consistent linear system. There's a pivot in every row of A. And you can also say that the columns of A span Rm, right? We have one pivot in each row, and there are n rows. And yeah, it's the existence. So it's, do we have a solution or not? If A is 1, 2, then we do have at least one solution for every B. Okay, and then 1 to 1 is uniqueness. So 1 to 1 means that every column of A is pivotal. So we have no free variables. The columns are independent, and we have at most one solution. So that we don't have more than one solution. We don't have any free variables. So that's what 1 to 1 is. And yeah, good way to memorize it is 1 to 1 is you can't have more than one. Okay, so that's module 1. Are there any questions or any suggestions for how I could do this better?
So far, it seems like it's good.
Okay. All right, I'm gonna move on to module 2. Taking this about 30 minutes, but I don't think module 2 is as long. So module 2 starts off with matrices, zero matrices, identity matrices, diagonal matrices, zeros have zeros everywhere. I already explained identity, and then diagonal is you only have non-zero entries on the main diagonal. I'm pretty sure all of you know how to add matrices and multiply them by scalars. Also with multiplying matrices, make sure the number of columns of the first one is equal to the number of rows of the second one, and don't mess it up like I did like a couple minutes ago. And I'll actually show you a neat trick I use for multiplying matrices that can speed up hand calculations. To be honest, I use MATLAB to do most of my matrix multiplications, but yeah, let me show you it. It's pretty simple, but I really like it. It really helps. So let's say we have this matrix right here. So let's say we want to multiply this matrix 2, 3, 1, 4, and then we want to multiply it by, it's a little thick, 2, 3, 1, 4, and then we're going to multiply by, the product has to be defined, so we're going to multiply by -1, 0, 2, 4, 1, 3. Well, the simple way to do it, the way I like to do it is I'm going to drag this matrix above, and now it's just like taking the dot products of each row and column. So we're going to do here and here for the first entry. So -2 plus 12 is 10, and then we can do this and this, and we get 3. And then we can go so on and finish out the product. This is really helpful because if this doesn't stretch out as far as this, like if we have an extra row up here, like then this is 3 long and this is 2 long. You can't take the dot product. The matrix product is not defined. This is also very helpful so you can see the dimensions of the product. And it's also useful if you want to multiply like 3 matrices. So say this is A and B, and you want to multiply A, B, and then you have a third matrix, C. Well, you can take this matrix and then go here. I use it all the time. It's really nice. But yeah, I digress. So, yep, I already talked about the dimension of the product. So left versus right multiplication, just know multiplying matrix on the left side is not the same as multiplying on the right side. You can't switch the order. But matrices do have the distributive properties, so you can the distributive property still holds. Just make sure you're not like doing left. You're not doing right when you're supposed to do left, and you're not doing left when you're supposed to do right when you're distributing. And no zero product property. So this means that if you have AB equals AC, that does not imply B equals C. Or if you have AB equals 0, A or B don't have to be 0. Both of them don't have to be 0. So don't like cancel out. So yeah, don't be careful when you're canceling out. The matrix transpose, I don't know how to do that. The rows become the columns, etc. The transpose properties, you can, the sum of the transpose of the sums is a sum of the transpose. You can also, scalars still work, scalar multiplying still works. And then this is the most important one. The transpose of A times B is the transpose of B times the transpose of A. So you're switching the order. And that's also the same thing for matrix inverses, which I'll get into in a second. And then, yeah, matrix powers, just multiplying a matrix by itself. So invertibility, 2 matrices are invertible. First of all, they have to be square. There are like rectangular, but that's beyond the scope of this course, as Dr. Mayer likes to say in the lectures. So square matrices are invertible when their product is equal to the identity matrix. So if AB equals BA equals I, then the A and B are invertible. There's a lot of properties. You can find them in your notes at the beginning of module 2. But the most important one, again, is the inverse of the product is the product of the inverses in reverse order. Make sure you know singular. Singular is not invertible. Don't mix them up. I did on the written assignment once. Didn't really affect that much, but it's just annoying. So singular is not invertible.
So
Yes?
So does every square matrix that has a pivot in every row / column become invertible?
Yes.
And is that also prerequisite?
We'll get into the matrix invertible theorem in a second, but yes, if a square matrix has a pivot in every row / column, then it is invertible. If not, it's not invertible. But we'll get into the theorem in a sec. But invertible versus singular matrices, oh, I already said that. Inverse of a 2x2, there's a simple formula for that. On the main diagonal, you switch to entries, and then off the main diagonal, you make them negative, and then you divide by determinant. I'll just show you the formula. Oh wait, I need a screen share again. Screen share, OneNote. Let's see, linear algebra and inverse of the matrix. Yeah, this is the formula I am talking about. To find the inverse, you just, for the 2x2, instead of doing the other method, which takes a little bit longer, yeah, you divide by the determinant and you switch the ones on the main diagonal, make the other ones negative. Stop share. Share screen again. Let's see, final review sheet. Inverse of the n by n matrix. So basically, you augment the matrix with the identity matrix. So so if you want to find the inverse of A, you augment it with the identity matrix, and you just row reduce. And you want to row reduce until on the left side you have the identity matrix, and on the right side you'll have A inverse. And you know the matrix is singular if you don't get the identity matrix on the left side. So maybe you're missing a pivot, or you have a free variable, or something like that. Yeah, that's how you can tell. That's one way you can tell how a matrix is singular. Another way you can tell, we'll get to that next. But another way you can tell if it's singular is the invertible matrix theorem, that giant, like 24 part theorem. Really everything is kind of the same. Yeah, it looks a little complicated when you first look at it, but really what it's just saying is if you have a pivot, since it's a square matrix, pivot in every row or column makes it invertible. If you have free variables or you're missing pivots, it's singular. So yeah, and you can also define the inverse using elementary matrices. If you're like it's more theory, but make sure to know elementary matrices. Those are just matrices that represent row operations. So like if you want to represent swapping the first and second row, you take the identity matrix, you swap the first and second row of the identity matrix, and now you get the elementary matrix for the row swap. And really when you're row reducing, you're multiplying both sides by an elementary matrix, which does the row operation. And all elementary matrices are invertible themselves. Okay, so next topic, there'll probably only be one, maybe two on partition matrices. But yes, you can treat, like, if you have like a large, you can treat a matrix as like a matrix of matrices. So you can, like, if you have like, yeah, so like you could have like, Control B, A, B. So like this would be a partition matrix. You have like A on this side and B on this side. But you could like, yeah. And the useful thing is if you have large matrices, you can split them up, and you can multiply partition matrices, and you can also compute inverses using partition matrices. I believe it's section 2.4, so I don't want to spend too much time on it because it's not going to be covered that much. Block diagonal matrices, those are just partition matrices where you have 0 matrices everywhere but the main diagonal. And they're only invertible if every matrix on the diagonal is invertible. Then the LU factorization, this is another one of those topics where there's only going to be one or two, probably only going to be one or two topics. Make sure you know upper triangular has zeros below the main diagonal, and then the lower has zeros above the main diagonal. And to construct it, yeah, make sure you know how to construct it. You're basically row reducing L, define L, you're finding the sequence of row operations that reduces A into U, I believe. I could check my notes, but, U is just the echelon form of A. Make sure you know how to solve linear systems using LU. So the nice way to think of this is, you know that, so if you're trying to solve AX equals B, you can substitute LU for A because A is equal to LU. You have LU equal X equals B. And then since by matrix properties, you can think of this as L times UX equals B. And we can say, oh, UX is Y. So UX would be Y. So first you solve UX equals Y. Or first you solve LY equals B, and then you use this Y and put it into this Y and solve for X. You can, yeah. And then also,
are there any
yes?
constraints when it comes to using LU?
Yeah, there's there are lots of constraints with LU. Yeah, like whatever you're given in LU in this course, you won't have to worry about that.
I mean, like when constructing it, is there like a specific matrix that can be constructed into LU only, or is it any type of matrix?
Specific. So like you're talking about the matrix A that you're trying to decompose into LU. Yeah, that's like I'm gonna check my notes real quick to make sure. But yeah, there are lots of constraints, but they aren't really covered in this course. Yeah. So, oh yeah, it says if A is an n times n matrix that can be row reduced to echelon form without row exchanges. So don't exchange rows, and also avoid multiplying by scalars. So the only thing you're doing is adding multiples of rows to each other. Yeah, let me make that clear. Your only thing you're gonna be doing is adding multiples of rows to another row, whatever it's called, row replacement. Don't, like, at least for this course, don't do anything else. Yeah. Yeah, you can review your notes. But yeah, the LU, it's only like it's a very small section. So you can check your notes to make sure you've got all the things you're required for the LU. Does that make sense?
Yeah, thanks.
Yeah, and then another small topic is everyone's favorite, Leontief. Make sure you're probably gonna be 1 or 2 questions at most again. So make sure you know the main thing is the equation, and which is x minus cx equals d, and x is your output vector, c is your consumption matrix, and d is your external demand vector. The next topic is computer graphics. Homogeneous coordinates, that's where you have in R2 you would have x, y, comma, h, and h would be just a number, most commonly 1, and it's used for translations and then rotations around a point. So when you're doing a rotation around the point, first you translate your vectors to the first you translate your vectors, first you translate that point to the origin, then you do your rotation, and then you translate back. Data matrices, that's if you have multiple points, multiple vectors, and so the data matrix, each column will be a vector. So it's you're transforming multiple vectors at the same time. And then 3D transformations, those are the ones in R3. Those ones you're basically going to be constructing with standard vectors. The main ones are rotations. So if it's asking you rotation counterclockwise at around the x-axis, you're going to look look from the positive side of the x-axis and rotate counterclockwise. Yeah, some 3D visualization. Yeah. So next part is subspaces and subsets. I saw a question last night on Discord. Someone was asking what these are. Subsets, don't overthink them. Subset is Subset is just a set of vectors. It's just a group of vectors. And the most important thing, and the real reason why we care about them is, let me fix this. Real reason we care about them is we want to know when a set of vectors, when a subset is a subspace. A subspace is a set of vectors, is a subset of Rn that is closed under scalar multiplication and addition. So if you add any two vectors in the subspace, the result will always be in the subspace also. And if you multiply any vector in the subspace by a scalar, then the result will also be in the subspace. And this also implies that the zero vector is always in the subspace, because if you multiply any vector in the subspace by 0, you'll get the zero vector, and that has to be in the subspace. So yeah, subspaces geometrically, again, think of them as like lines or planes. Lines would be ones that are spanned by one vector. Planes will be spanned by two vectors, and they're going to pass through the origin. Column and null space, they're another way to think of subspaces. Column space is the span of the columns of a matrix, and the null space is the span of the solution set of AX equals 0. And make sure you can construct bases using set builder notation. So that's when it says, oh, X is a vector in Rn with the little curly braces. It says X is a vector in Rn, and here are a couple equations, X1 plus X2 equals 0. And that, you can just think of those equations. I remember like, that was like module 2, and everyone, there's tons of questions on Piazza, myself included. And the good way to think of it is think of those equations as like a linear system and find the solution set, the null space, and that would be your subspace. And then what is the standard basis for Rn? Those are just the columns of the identity matrix. Also bases themselves, they are just a set of linearly independent vectors that span a subspace. So 0 vector cannot be in the bases. Zero vectors in every subspace, but it cannot be part of the subspace's basis. And subspaces can have multiple bases. They're not unique. And if you want to find a basis for columns for null space, it's just finding the solution set to AX equals 0. For column space, you want to find the pivot columns. So get the matrix in echelon form, find the location of the pivots, and then go back to your original matrix that's not in echelon form, and those columns and the pivot locations are your basis. Dimension is just the number of vectors in a basis. So like a line is spanned by one vector, and you'd have one vector in the basis, so the dimension of a line would be 1. I already explained how to find it for column space and null space. Rank is just a fancy way of saying the dimension of the column space. Rank nullity theorem tells you that the rank, which is the dimension of the column space, plus the dimension of the null space, is equal to n, the number of columns. It's just an extension of saying the number of basic variables and free variables adds up to n. And then you can use this information to determine if a square matrix is invertible as well. Also, a more minor section, know how to find coordinate vectors relative to the basis. So this is just saying I have vectors u and v, and w is in the span of u and v. What are the constants? What are the weights of u and v that you need to get w? And those weights form the vector themselves, which is the coordinate vector. Any questions?
To find the entire null space of a matrix, would you just set the matrix to 0? Like,
yes,
augment
to find the
matrix.
null space of the matrix, you are always going to find the solution set to AX equals 0. Do not find the solution set to AX equals B. Do not do that. Find the solution set to AX equals 0. Because if you want it to be AX equals 0. And that's why it's called null space, because like null 0, or at least that's what I think it's called. So so null space is AX equals 0. Yeah. All right. Module 3. Module 3 starts off with determinants. The determinant method, it's that one where you go down a row or column and you, I think all of you know the determinant formula. If not, you can review in your notes. But just know you can do it down, you can compute a determinant down any row or column. So if you have a column with like lots of zeros, that you want to use that column to find your determinant because you have much less work to do. And remember, a cofactor is when it's like you take one, so a cofactor for an entry of a matrix is you look at that entry, you cross out the row and column that the entry's in, and the rest and all the remaining entries form their own matrix. And then you also need to multiply by -1 to the power of, if you're in an, yeah. And then for a cofactor, also multiply by -1 to the power of m plus n. So if you're in the first, if you're in the entry in the first row and first column, that is 1 plus 1, 2, so you don't have a -1 multiplied. You can, yeah, it probably sounds more complicated by when I'm speaking a word, but yeah.
I have a quick question.
Yes.
So for a 3x3 matrix, there was something in the modules about like a diagonal method, and I didn't understand what that was. Can you go over that real quick?
I'm not sure what specifically you're talking about with the diagonal method.
It's for finding determinants.
For a diagonal matrix?
I'm sorry, my bad. It's for finding a determinant of a 3x3 matrix.
Oh,
using
that method.
The diagonal method.
There's a for a 3x3 method, a 3x3 matrix. There's another method you can use other than the standard one, but you can look it up and find it. But I tend to just use the normal one where you're finding with all the cofactors where you're multiplying by -1 and finding those like matrices inside matrices because that one applies to all matrices. Another thing you can use for everything is use MATLAB or Wolfram Alpha or something else to find this stuff for you. You shouldn't be asked to find like a determinant of a 4x4 or higher matrix unless they give you like a row with lots of zeros or something because it takes a while. So determinants of triangular matrices, those are also nice because determinants of triangular matrices, you just multiply all the entries on the diagonal. So yeah, that's nice. So row operations do change the values of a, row operations do change the value of the determinant and specific rules. So if you multiply one row by a scalar, then the determinant is going to be multiplied by that same scalar. If you swap any two rows, then the determinant is multiplied by -1. So you flip the sign of the determinant when you swap rows. And then when you do your row replacement where you're adding a multiple of one row to another, it doesn't change the determinant. So you could also find your determinant by getting down to echelon form and doing the triangular, doing the method for triangular matrices if you want another way to find the determinant. And yes, the rules for row operations also apply to column operations. So if you multiply a column by a scalar, then the determinants multiply by a scalar, etc. And the determinant of the transpose of the matrix is the same as the original matrix. It kind of goes along with take the determinant down any row or column. The determinant of the product of two matrices is the product of the determinants, and inverse is just determinant of A inverse is just 1 over determinant of A. And it's also another way you can figure out if a square matrix is invertible or not. The determinant is equal to 0. The matrix is singular. It's not invertible because 1 over the determinant, 1 over 0 is undefined. And then determinants can also be used to find area and volume. So for a parallelogram, that's two vectors form a parallelogram. Two vectors in R2 form a parallelogram. You just make those two vectors into a matrix, and you compute a determinant, take the absolute value, and you get your area. Parallelepipeds, those are just parallelograms in higher dimensions. So anytime it just says, oh, here are some vectors that form or span a parallelepiped, put those vectors in a matrix, find the determinant, take the absolute value, you get your area. Same with matrices for linear transforms, take the determinant. Determinant means area. Or volume. same thing, but like
Yeah,
different
I got a
dimensions.
question about
Yes.
triangle matrices. What would you say was the rule for determinants of those? I know it's simple. I just didn't hear what you said.
The rules for which matrices?
For determinants of a triangle.
Oh, triangular matrices, you just multiply all the entries on the diagonal together.
And then what did you say the property was for matrix multiplication with determinants and then
Oh yeah, so if you have A times the determinant of A times B, it's just the determinant of A times the determinant of B. Yeah. So yeah, the next section is we're getting Markov chains and eigenvalues. So make sure you know what the Markov chain is. The ones with the probabilities and stuff. The state vector is just your current state is just any x vector that's a probability vector. Probability vectors, the entries add up to 1. So you can think of each entry as a probability. The transition matrix is that matrix P. And transition matrix is same thing as the stochastic matrix. A stochastic matrix, its columns are probability vectors. So yeah, everything's probability vectors. All the columns add up to 1 for Markov chains. And a stochastic matrix is regular when any power. So you can take any power. All you have to do is find one power of that matrix, of that stochastic matrix that has no zeros. So yeah, I think some people get confused on it. Just usually it's if P has if P has a 0 entry and you find P squared and it doesn't have a 0 entry, an entry that's 0, then it is regular. All regular steady state vectors. Whenever you multiply the stochastic matrix by the steady state vector, you get the steady state vector back. You get the steady state vector back. So steady state, it doesn't change no matter how many times you multiply by that stochastic matrix. And you can, so regular matrices, regular stochastic matrices always have a unique steady state vector. So if the stochastic matrix is not regular, you may or may not have a unique steady state vector. It's like the identity matrix is a stochastic matrix, but the identity matrix, any vector times the identity matrix returns the same vector. So you have an infinite number of steady state vectors for the identity matrix. So calculation relation to eigen stuff. So calculation of steady state vector, that's just you're solving PQ equals Q. It's the same way you calculate eigenvalues, which we'll get into in a sec. And a steady state vector is an eigenvector of the stochastic matrix with an eigenvalue of 1. You may get asked like a question, there's just a chance you may get asked a question like that that's trying to make you think. So eigenvectors, all the eigen stuff. I remember eigenvectors is a vector where you where if you multiply it, so like an eigenvector, a v equals lambda v. So you can think of it as a vector where instead of multiplying by the matrix, you can just multiply by a scalar, and that scalar lambda is the eigenvalue for that eigenvector. Geometrically, think of it as vectors, like when you apply linear transformation matrix to a vector, and the vector only changes in length. It doesn't change in direction. That's the geometric interpretation for eigenvectors and stuff. So first, eigenvalues of triangular matrices. You can just pluck them off the diagonal. So all the entries on the diagonal of a all the entries on the main diagonal of a triangular matrix are the eigenvalues. And how does this relate to determinants? Because remember, determinant of a triangular matrix is multiplying all the entries on the diagonal together, and determinants and eigenvalues are related. What matrices always have an eigenvalue of 0. Matrices, those are singular matrices. And the matrices in all stochastic matrices have an eigenvalue of 1. But just because a matrix has an eigenvalue of 1 doesn't mean it has doesn't mean it's stochastic. But this one is an if and only if kind of thing. It's a singular matrix and the eigenvalue of 0 are like equivalent. Eigenvectors and linear independence. Eigenvalues that correspond to distinct eigenvalues are independent. So if you have an eigenvector v that corresponds to an eigenvalue of 1, and you have an eigenvector u that corresponds to an eigenvalue of 2, v and u are linearly independent. And yes, row operations can change the eigenvalues of the matrix. So you can use row operations for determinants, but don't use them for finding eigenvalues. They will mess you up. So eigenvalues can be determined using the characteristic polynomial. That is just your a minus lambda I, and you take the determinant of that. And you use that to solve for your eigenvalues. And you can, so another way you can look at eigenvalues is a trace of a matrix, which is the sum of the entries on the main diagonal. And that sum is equal to the sum of all the eigenvalues. It's really mainly useful when you have a 2x2 matrix and you know one of the eigenvalues and you can find the other by subtracting that one from the trace. Probably should mention finding eigenvalue and finding eigenvectors. So once you have your eigenvalues, so you have your a minus lambda I, but now you know your lambdas. So let's say you have lambda equals 1 is an eigenvalue. So you would find a minus 1i, you'd find the null space of that matrix. That gives you your eigenvectors that correspond to the eigenvalue. Yeah, some of this stuff probably sounds more complicated because I'm like saying it only by word, but you can always review your notes and look at the formulas. Yeah, so now we're going to talk about algebraic and geometric multiplicity. Algebraic multiplicity is just the number of times the eigenvalue appears in the characteristic polynomial. So if you have, for example, lambda minus 1, all that squared equals 0, then lambda equals 1 has an algebraic multiplicity of 2. Geometric multiplicity, that is just the dimension of the eigenspace for an eigenvalue. The eigenspace is just the eigenspace is just all the eigenvalues. Is just the set of all eigenvalues for an is a set of all eigenvectors for an eigenvalue. So that's the null space of a minus lambda I. And that dimension, so it's like it's basically the number of independent eigenvectors that can correspond to just one eigenvalue. And that dimension is less than or equal to the algebraic multiplicity. But you can't have a geometric multiplicity of 0 because that means you only have the 0 vector as an eigenvector, but we don't consider the 0 vector to be an eigenvector because, it works for every eigenvalue. So your geometric multiplicity, or dimension of the null space of a minus lambda I, has at least a dimension of 1, but no more than the algebraic multiplicity. Obviously, the algebraic multiplicity can't be bigger than the size of the matrix. So the maximum algebraic multiplicity for an eigenvalue of a 2x2 matrix is 2. For a 3x3 matrix, 3. So that's eigen stuff. I should have changed this to eigenspace up here. That's why I forgot to mention eigenspace sooner. So how can eigenvectors be used to determine the long-term behavior of Markov chains? That was in worksheet written assignment 3. That's that question at the end where you have to find the limit. You can review that, but basically you're representing any probability vector by a sum of the stochastic matrices eigen vectors, and you use the formula. Also make sure you know all the eigenvalue rules, like a squared, like the eigenvalues of a squared are the squares of the eigenvalues of a, and for a inverse, it's 1 over the eigenvalues of a. When are two square matrices similar? If you can write them as a equals pb p negative 1, and b doesn't have to be diagonal, but here B is diagonal. And similar matrices can, in similar matrices, they have the same eigenvalues. They have the same characteristic polynomials. But just because two matrices have the same eigenvalue doesn't mean that they're similar. So it works in one way, but doesn't work in the other way. So next, diagonalization. That's just an extension of similarity. Diagonalization, it's A equals P D P negative 1, where D is a diagonal matrix. And matrix is only diagonal if all of its geometric multiplicities are equal to their algebraic multiplicities. So that means you have to have n independent eigenvectors. Otherwise, if that's not true, you can't make your P matrix because your P is those eigenvectors, and then the D, the entries in the diagonal of D are your eigenvalues. And P, DP, negative 1, decomposition, diagonalization is really useful because you can easily compute matrix powers with it. So yeah, so next, complex numbers. Make sure you know what conjugate is. So like conjugate of A plus BI, or wait, before I get on to that, any questions on eigen stuff or Markov chains? Okay. Complex numbers, conjugates, like the conjugate of A plus BI is A minus BI. The absolute value of A plus BI would be it's A squared plus B squared. Let me see, let me check if it's complex eigenvalues. The absolute value would be the square root of A squared plus B squared, but I'm pretty sure you won't have to find that at all for this course. Polar form is just, you know, you find square root of A squared plus B squared is R, and then theta is inverse tangent of B over A. But the most important thing is, what's important for this course is using complex, is eigenvalues that are complex. Complex eigenvalues always come in pairs, and their pair is, it's like if A plus BI is an eigenvalue, then A minus BI is also an eigenvalue. Their conjugates are eigenvalues too. Rotation dilation matrix, that is just a matrix in the form of, I'm gonna switch over, stop share screen. So a rotation dilation matrix is A, negative B, B, A, and you can easily figure out the eigenvalues of this matrix. The eigenvalues are lambda equals A plus or minus, write that better, A plus or minus BI, and you can find the angle of rotation by doing inverse tangent of B over A. I'm probably triggering some people who would prefer to use arctangent, but I don't care. And then so that's theta, and then the dilation factor is your square root of A squared plus B squared. So yeah, that's rotation dilation matrix. Share screen. Oh wait, I just shared the same screen. That was not good. Here we go. Here we go. How do you find the PCP negative 1 decomposition of a 2 by 2 matrix? That your P is the, so that's the one where you're finding the eigenvectors for A minus BI. Yeah, it's a, actually, I'll just switch to my notes so I can show you the formula so I don't have to say it out loud. So it is down here. So V would be the eigenvector associated with A minus BI, and P is the real component as your first column, and the imaginary component of that eigenvector as your second column, and then the C matrix in the middle That is, you're looking at the A minus BI, and you're putting those A and B values into this rotation dilation matrix. So stop share screen again. Okay, next is more stochastic matrix stuff and Google PageRank. So all the eigenvalues of a regular stochastic matrix are less than or equal to 1. Remember, all stochastic matrices have an eigenvalue equal to 1, so its other ones are less than 1. And then if you take that stochastic matrix and you keep multiplying it by itself, eventually its columns will become its steady state vectors. So P is this limit pi, this capital pi will equal Q, Q, Q dot 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 Q. So like all the columns will be the same. They'll be the steady state vector. And same deal here. If you do the same thing, but also multiply by any probability vector, so P is a regular stochastic matrix and X is any probability vector, you will get the steady state vector. So that's a nice way for dealing with Google PageRank, which we'll talk about next. Make sure you know the meaning of Google PageRank, the assumptions that are used in the initial form, know what importance is, the probability of each page being selected, and then you rank the importances to give you PageRank. And then in the lecture, they go on and say, here are 2 adjustments that you can make to improve PageRank, and that's dealing with the websites with no links to other pages and the damping factor. It's going to be a little bit annoying to explain out loud, so you can look at your notes and review this stuff. Oh yeah, also the Google matrix, know what the formula for that, and the Google matrix is regular stochastic in addition to being stochastic. Hey, any questions on module 3?
So are all the values of a regular stochastic matrix less than or equal to 1, or all the eigenvalues?
All the eigenvalues, but actually both, because the entries, because each column, all the entries in each column must add up to 1 for it to be stochastic.
Okay, thank you.
Yeah, there's a question in the chat. Can you go over using eigenvalues and eigenvectors to find Markov steady state? Yes, I will. I will pull up my written assignment 3, linear algebra, written assignment 3. Stop share. Let's share WA3.